Hello everyone, today we shall discuss about the physics of spheres, surface tension and axis pressure. Why is a drop round? It is the result of a silent, constant battle between two invisible forces. Internal pressure pushing out and surface tension pulling in. This deck deconstructs the geometry of liquids, moving from simple surfaces to complex bubble interactions to derive the governing laws of hydrostatics. The spherical imperative. You see, if external factors like gravity are negligible, liquid drops naturally assume a spherical shape. The principle of minimization. A free liquid surface seeks the minimum possible surface area for a given volume. Geometrically, the sphere possesses the least surface area for a fixed volume. The indication of pressure. The bulging shape of a drop is not passive. It signals that there is an excess pressure inside the drop compared to the outside. So you can say that pressure inside is greater than pressure outside. The geometry of forces, plane surface, resultant force 0. Here you see that the golden rule to maintain equilibrium, there is always an excess of pressure on the concave side of a curved surface. Here also see this is on the curved surface, the pressure, the force is in this resultant in this direction. Here also you see this is the convex surface, but the force is in this direction, right? So the pressure is here and the pressure is in this direction. So you can say the golden rule, to maintain equilibrium, there is always an excess of pressure on the concave side of a curved surface. Defining the flares. You see, this is the internal pressure, this is the radius, this is the surface tension, and this is the external pressure PO or P outside, right? So we calculate excess pressure delta P by balancing the forces at play. R radius, the curvature of liquid interface. T the surface tension, the cohesive force acting along the surface trying to contract. Pi internal pressure, the pressure inside the sphere. Po external pressure, the ambient pressure outside. Delta P excess pressure, the difference between needed to maintain Pi minus Po. Case study 1, the liquid drop. Force, excess pressure into area. Force equal to tension into circumference. A liquid drop has one visible surface, liquid inside, air outside. To analyze the forces, we conceptually slice the drop in half and look at the equilibrium of the hemisphere. Projected area pi r square and circumference is 2 pi r. So what we are getting here, the balancing act derivation. For the drop to remain static equilibrium, the outward pressure force must equal the inward tension force. Outward force, pressure F, pressure, excess pressure into area, delta P into pi r square. Inward force, tension, F tension, surface tension into circumference, that is T into 2 pi r. Equilibrium. So we are getting delta P 2 pi r square equal to 2 into 2 pi r. So in the conclusion we get that delta P equal to 2T by r, where T is the tension, r is the radius. This we get delta P as 2T by r. Here you see the air bubble, or we consider it the cavity. An air bubble inside a liquid, a cavity, is physically identical to a liquid drop in air. Why? It possesses only one free surface or interface. The liquid is outside, the air is inside. Because the geometry is the same, single interface, the physics remains unchanged. So the formula delta P is equal to 2T by R. Case study 2, the shock bubble anomaly. Here you see, unlike a solid liquid drop, a shock bubble is like a blown up balloon, a thin film of liquid with air on both sides. The critical difference, this film naturally creates two free surfaces. The inner surface in contact with the trapped air and the outer surface in contact with the ambient air. You see, this is a thin liquid film, this is inside air, this is outside air. The double interface changes the force equation significantly. What we get, doubling the tension. That is because there are two surfaces. Surface tension acts on both the inner and outer circumference of the film. The new force equation. Outward force unchanged P equal to delta P into pi r square. Inward force 2 into 2t and pi r. So it is 4 pi rt. So the in equilibrium we get delta p 2 pi r equal to 4 pi rt. So you get delta p equal to 4t by r. So in the case of these, in this case we'll get delta p equal to 4t by r. And you see critical compression drop versus bubble. Either it is a liquid drop or a cavity, delta p is equal to 2t by r, but in case of bubble it is just two interfaces, delta p equal to 4t by r. Confusing a drop with a bubble is the most common error in hydrostatics. Always count the interfaces. Solid mass 2t by r, thin film 4t by r. This is advanced interaction, the double bubble. Consider two soap bubbles of radii R1 and R2 where R2 is less than R1 formed of the same liquid. When they merge to form a double bubble, they share a common internal film. The question, why? Which way does the common film cut? Does it bulge into the large bubble or into the small one? Radius of the common interface. To find the radius of curvature R of the common film, we calculate the difference in excess pressure. Equation: the excess pressure of the interface is the difference between the two double pressures, that excess pressure P2 minus P1. Substituting, get 4t by r equal to 4t by r2 by 4t by r1, or simplifying that 1 by r equal to 1 by r2 minus 1 by r1. And summary and key takeaways. Liquid or air cavity, one surface, excess pressure is 2t by r. Soap bubble, two surfaces, so excess pressure is 4t by r. Merged bubbles, pros high to low pressure, 1 by r equal to 1 by r2 minus 1 by r1. Physics of shape. Surface tension minimizes area. Pressure is always higher on the concave side. The scales of equilibrium. From the dew on a spider web to the industrial formation of foams, the simple laws of equilibrium govern the behavior of fluids. By understanding the relationship between radius, tension and pressure, we unlock the ability to predict and model the shape of the liquid world. Thank you everybody for watching this video.